Okay, so we're going to practice writing net ionic equations. And I got a remind from somebody asking, are we doing this for the final or for the next test? And the answer is yes. So we'll be on the final, but we're also doing this for the next test.
Really quickly,
the next test is on chapters 5 and 7, and this is chapter 5. So there are 5 equation types: synthesis, decomposition, typically not happening in water; combustion, pretty much never in water. But single displacement and double displacement do happen in water. And so for those, we can write more than just the molecular one that we use for stoichiometry. We can also use our solubility rules or our table of electrolytes. We use those, refer to it interchangeably that way. It's basically what electrolytes are just things that can carry charge, so ions. And table of electrolytes and solubility table are both saying what things break into ions or can be pulled into ions. Let's look at this table and see. And then once we've used that table, we cross out spectators. And a spectator is just something that hasn't participated in the game. It's something that is the same on the left and right of the arrow. And that gives us our net ionic. And so the net ionic, the molecular is important because this is the one we use for stoichiometry, which is using a balanced chemical equation to make predictions about how much product can be produced or how much reactant is needed. The total ionic is just a vehicle to get to the net ionic. The total ionic tells us how things actually exist in solution. Are they molecules that are dissolved? And that could be something like carbon dioxide, sulfur dioxide, water. Acids would be molecules that are dissolved. There's one base, ammonia, that is a molecule that can be, or ammonium hydroxide, that can be dissolved. And then there's things that don't even dissolve in water. We call those precipitates, insoluble solids. So the total ionic is just looking at how things actually exist in perhaps the 2 jars or bottles before we combine things. And then once we combine things in the final beaker or flask. The net ionic tells us the chemistry. This is about the chemistry that happens. And since we're taking a class called chemistry, that is probably important. Uh-oh, we're talking about in water. Let me add some water. There we go. Okay, so this worksheet today is just writing net ionic equations is a chance for us to practice how to do these things with the 4th and 5th kind of equation. And so the first thing is to write the correct reactant formulas, which means nomenclature. And you're about to take an exam on this. And for the exam that we're taking, the 4th exam, and for the final, if you were to like Google nomenclature, that's cheating. So don't do that. But definitely have your notes out so that you can start with the correct formulas. And then the second step says, for a single displacement reaction, you have to check and see if it even happened. So for this one kind of reaction, there is a table, and the table shows you, here I have a metal, and in a different column, we have that metal's ion. And if I have a metal in this column and an ion in that column, and those are my reactants, and the one on the left is higher, that reaction goes. Oh, you can't see it. Yeah. Thank you. I was drawing this picture here. I was just saying we have a table, and if the metal that is a reactant is higher than the ion that is a reactant, the reaction goes. But if we have a metal and a metal ion that are arranged thusly, so these are both reactants, the reaction doesn't go. And so we only use that table for single displacement reactions. Okay, then if a reaction does occur for single displacement or always for a double displacement, we now can predict the products. And so we do some substitutions. Then we add coefficients, step 4, to balance the equation. And once we have, a balanced molecular equation, we would stop there and use that for stoichiometry. But for our next exam, the written part of exam 4, which is on chapter 5, you're gonna, to this molecular equation, use your table of electrolytes and decide, how things exist to get a total ionic equation, and then cancel spectators to get the net ionic equation. And so I was just gonna start at the top and walk through. I'm gonna do this one. If you have questions, you'll ask, and then I'll do the next one, et cetera, et cetera. If you had already done these, that would be helpful. If you've already done these, you're gonna find that you've made mistakes because you're just learning chemistry in this class. That's the reason you're in this class, and it's normal to make mistakes. But don't freak out. Just ask questions and make sure you make notes. And you can use this. I wouldn't use this. I mean, you can use these prompts and then what you've written, your notes on the exam. That is not cheating. If they're your notes that you wrote, you're just using the resources that you've made yourself. So if there are no questions, I'm going to go ahead and get started. Let's see who's here. Okay. Alrighty. Number one, calcium chloride and potassium phosphate. So the first step is to write the correct reactant formulas. Calcium's +2, chloride's a -1. We need 2 of those. Potassium's a +1, phosphate's a -3. We're going to need 3 potassiums. And now we're going to predict, oh, this is a double displacement reaction. How do I know that? If it were a single displacement, how would I know that? She asks herself, and then she answers. Double displacement starts with 2 compounds. The single displacement would have an element and a compound. Okay, so I can skip step 2 because this isn't the SDR. I'm going to predict products by putting the cation of the first with the anion of the second. Calcium is a +2, phosphate's a -3. So I'm going to shoot for 6. I need 3 of these and 2 of those. And then the cation of the first, the anion of the second. Potassium's a +1, chloride's a -1. The correct formula has the cation before the anion in a 1-to-1 ratio. Then we can make 6. Okay, so now I need to, step 4, balance the equation. Whoops, I already did. When I was putting the salt together here and I saw that 3 and this 2 told me to write a 2 there, and that 3 told me to write a 3 here. Now I'm gonna, to my molecular equation, use a table of electrolytes to decide if things stick together or break apart. These are all salts. So I'm looking at the rules at the bottom, which only apply to salts. What's a salt? It's an ionic compound that isn't a hydroxide. Okay, chlorides are generally soluble, except for 3, and this isn't one of the 3, so I'm going to break it apart. 3 calcium ions, ions have charge, and 6 chloride ions. Potassium phosphate, potassium ions are always soluble. Love that rule. 6 potassium ions, 2 phosphate ions. Calcium phosphate. Phosphates are generally insoluble. That means make a precipitate, a solid, except for alkali metals and ammonium. But calcium is not an alkali metal, it's an alkaline earth metal. So this is a solid, it does stick together. This is our precipitate. And 6 potassiums, always soluble, 6 chlorides, usually soluble, only 3 exceptions. So now number 6, to the total ionic equation, cancel spectators and rewrite. Chloride hasn't changed. Potassium hasn't changed, ion hasn't changed. So 3 calcium ions, 2 phosphate ions. If I'm to form calcium phosphate. It is possible that everybody has already done number 1. There are no questions, but as I go, if you have questions, if you didn't come with these all done, it's totally fine. I sprung it on you an hour ago. So we need to check charge balance and mass balance for the reactants and the products. So calcium, phosphorus, oxygen, and charge. For mass balance, I have 3 calciums on the left because of this 3, and 3 calciums on the right because of that 3. 2 phosphoruses on the left, 2 phosphoruses on the right. 8 oxygens, 2 times 4 on the left. 8 oxygens, 2 times 4 on the right. The charge on the left is 0 because I have +6 and -6. And then we have a compound on the right. So this is a balanced equation. Questions?
Wait, I'm sorry. Where did you get the +6 and the -6?
Yeah. It's kind of messy here. Let me clean this up a little. Okay. 3 times +2 is +6. 2 times -3 is -6.
Okay, that makes sense. Thank you.
Good. Thank you for talking to me. All righty. I want to clear my board unless you tell me not to. Oh, look, I have another page. If you need me to go back, I can. Number 2 says silver nitrate and copper metal. Copper metal is an element. Silver nitrate and copper metal. So I need to find copper, because it's the solid, above silver ion on my chart to decide if this happens. See if I can find a chart somewhere.
So, Sue, how do you know which way to go on the chart? Like from which metal to which metal, I mean? Like which one, how do you know which one comes first?
That's a good question. The one that doesn't have a charge comes first
So the copper comes first.
because it doesn't have a charge. Right.
Okay.
There's a chart. Yeah. Right. So because copper doesn't have a charge, it's the one that needs to be in the left-hand column. See how everything in the right-hand column has charges?
Yes.
Okay. And so is copper above silver ion? Here's copper. Here's silver ion. This reaction goes. When copper becomes an ion, it's going to have a +2 charge because that's how it's written on this chart. And I'm limiting our conversation to this chart, which will be something that you need to have handy, and it will be provided when you take the test. When silver ion gains an electron, it will be silver metal. Okay, so this reaction does go because copper is above silver, things roll downhill, that means reaction. Good. So copper is going to replace silver ion. Oh, that's a problem. Thank you. Copper is going to replace silver ion and become copper 2 nitrate. And then silver is going to become the metal, the solid. Okay, because of this 2, I need 2 of these. If I have 2 nitrates, I'm going to have 2 silvers. And then 2 silvers, 2 nitrates, 1 copper, 1 copper. I think we're balanced. So go ahead and check charge and mass balance. I think we have a balanced equation. Now we're going to go ahead and apply the solubility rules. Are nitrate salts soluble? Yes, always. I love that rule. Don't forget that this too applies both to the silver ion and the nitrate. Does anything cancel? Just the nitrates. Does copper cancel? No, because copper without a charge is different than copper ion. Copper 2 ion is a different thing than copper metal. And rewrite what's left over. I give you permission not to write aqueous, but any other state, solid, liquid, or gas, you need to write. You have the table of solubilities, that shouldn't be a problem. Okay, the next one, sodium sulfite. Ites are 1 oxygen fewer than 8s. And hydroiodic acid. Hydroic acids come from ides. My ride has hydraulics, hydroics. Is this an acid-base reaction? Nope. We've got a salt and an acid. But that means that we're going to have to look at 2 places on our chart. Only the salt rules apply to salts. I mean, salt rules only apply to salts. And there's a whole column, 3 columns really, for acids. Okay, but still, this isn't single displacement because I have 2 compounds. Cation of the first, anion of the second. Cation of the second, anion of the first. Sodium's a +1. Iodide's a -1. They come together in a 1-to-1 ratio. Sulfite is a 2, and hydrogen ion's a 1. So I'm going to need 2 of these to make H2SO3. Sulfurous acid. Is this equation balanced? Not yet. I need a 2 here. Okay, so I don't know because I can't see a lot of faces if I'm going too fast. Did you do them already? And I'm going too slow. So unless you type in chat or tell me to slow down, I won't know.
I think your pace is good. Thank you.
Pace is fine.
Okay, I will keep going. So sodium salts are always soluble. Love that rule. So sodium sulfite makes 3 ions, 2 sodium ions and a sulfite. Hydroiodic acid, is that a strong acid or a weak acid? We don't have any insoluble acids in our class. The reason I ask is if it's a strong acid, we're going to break it into ions. It ionizes 100%. But if it's a weak acid, we'll keep it together.
Strong
Yeah.
acid.
It's one of the 6 strong acids. Good. And the 2 applies to both the hydrogen and the iodide. Okay, sodium salt's always soluble. Love that rule. Favorite rule. Sodium tastes good. Sodium ion. I don't recommend eating sodium. And then this second acid, sulfurous acid. Anything important about that?
Doesn't it break down to water and SO2?
That's right. It's one of the 3 gas-forming products that you need to know. Good job. Okay, so there's my total ionic equation. Are there any spectators? Yes, Sue, I see sodium ions on both sides. Thank you very much. Yes, Sue, look at those iodides. Okay, cross them out. Rewrite what's written. As a matter of habit, I put the cations on the left. You don't have to. This would be completely fine. It just feels wrong to me. Ah, I can't stand it. If the state isn't aqueous, I want you to state the state. And then check for mass balance and charge balance. Okay, number 4, ammonium nitrate. +1, -1. And sodium bromide. +1, -1. 2 salts, this is double displacement. For an acid plus a base, double displacement. Salt plus acid, salt plus base, double displacement. So predict the products. Oh, look, it's already balanced. Because they're all +1s. Okay, so do you think I need to write a total ionic?
You can, but they're all going to cancel out.
They are, that's right, because nitrates are always soluble. Ammonium salts are always soluble. Sodium salts are always soluble. The answer is no reaction. So you don't have to do all that work. You can just write no reaction. Okay, the next one, sulfuric acid and calcium hydroxide. This is a acid-base reaction. And the question is, how many waters can I make? And I would say 2. I've got 2 hydroxides and 2 acidic hydrogens. We're going to make 2 waters. Now we need to look at all the rules. Here we have an acid. So check the acid rules to see if it's strong. We have a base. Check the base rules to see if this hydroxide is soluble. We have a molecule. This is covalent, and it's water. And water will need to be a liquid. And then we have a salt. So we need to check the rules at the bottom to see is that salt soluble or insoluble. Sulfates are usually soluble, but there are some exceptions. What does it say about with the acid?
It says just the first H.
First proton only, okay. So I'm gonna write it this way. Good. It is a strong acid, but only the first proton. How about the base?
Soluble.
It's soluble.
Okay. So how many ions does that break into?
2.
2 kinds, 3 ions, yes.
Oh, okay.
Okay, water is covalent, so I'm gonna write H2O liquid, keep it together. The only covalent species that we would ever write as ions are strong acids. Strong acids can be ionized in water 100%. Weak acids are ionized a little bit. They can do some chemistry, but if they're by themselves, they stick together mostly. Okay, calcium sulfate, is this a soluble salt?
No.
No, keep it together and write solid. Okay, there's our total ionic equation. Anything we can cancel? Nope. The next one is an acid-base reaction too, hydrofluoric acid and sodium hydroxide.
Wait, what are those acronyms that you just wrote? Like, what does that stand for?
Total ionic equation equals net ionic equation. What that
Okay.
means is nothing canceled.
Thank you.
The other choice that we saw is everything canceled. So there's 2 extremes. Okay. Hydrofluoric acid. Hydroic acids come from ides. Fluoride, hydrofluoric. And sodium hydroxide. Make 1 water. Cation before anion.
Sue, I have a quick question.
Uh-huh.
Why aren't you writing H2O for both the top and the bottom?
Yeah. So when I'm predicting the products, what I need to remember is that this hydrogen is part of a hydroxide and that this hydrogen came from a different source. So that's the reason that I write it funny on the first line.
So then we can turn it into H2O after?
Sure. If you know what you're doing and you want to write H2 at the beginning, that's fine. Like if you wrote this here, that's fine. But there are some students that still don't realize like H2, oops, try again. H2 and OH 2 of those, they wouldn't be sure how many of these to write. Like they're not sure what to do because it looks like I have an H2 there and an H2O here, and then I'll have an extra H or something. So when we first learn how to balance these, that's why I wrote it that way. If you're past that, don't write that. If I wasn't talking to a group of beginning students, I wouldn't write it that way, HOH. Okay, so now we need to decide, this is an acid, strong or weak. This is a base, strong or weak, or insoluble. Here's a salt, what to do with that?
I think the acid is weak.
Okay, so how do you want to write it on the next line?
Mm,
Keep it together.
that's
If
what I
you-
was gonna say, but I was scared.
Yeah, and how about that base?
It's strong.
Mhm. Strong enough to stand alone. I don't need you, counter ion. Okay, and the salt? We don't know about fluorides, but we know sodium salts are always soluble. That's a good rule. Anything to cancel?
The sodium.
Sodium.
The sodium. And rewrite what's left over. So for the net ionic equation, it is possible, nay, likely, that there is an overall charge and it isn't 0. And here the overall charge is -1 on both sides. For a molecular equation, these are things that don't have charge, things need to be 0. For the total ionic, where we have ions and counter ions, those will be 0. But for the net ionic, you can have a non-zero overall charge on the left and the right. They just have to be the same. Okay, the next one says elemental copper element and hydrochloric acid. So this is single displacement. We need to look at the table and see if it even happens. Here's copper metal. Here's H plus for acids. No reaction. Okay, number 8, we have zinc and iron 2 nitrites. So we need to look at zinc and iron 2. And if the placement is like that, there is a reaction. And if the placement is like that, there is no reaction.
There's a reaction.
Okay. Iron 2, oops, and zinc. Okay, so zinc is going to become zinc ion, and iron 2 ion is going to become iron metal. We don't have a rule about nitrites, but let's say they're soluble. Sometimes students will do this thing, and the other instructors and I often go, why? Why? But we see it every semester, and that is they'll start with zinc with no charge in a molecular equation as a reactant, and on the next line, suddenly it's +2, and that doesn't make sense. It could be +2 on the other side, sure, because this is a before and an after, and it's lost electrons. But the befores can't change. Before have to all be the same. Okay, calcium and water, number 9. It's not calcium something, so it's just calcium metal. And I want to change how I write water on this one for sure. Actually, I'll do it both ways. So metal plus, if it's a really reactive metal, if the acid is even just water, which isn't technically an acid, it can still react. And that's what's happening here. So for us in our class, sodium, potassium, and calcium are so reactive that they will react with one of the hydrogens in water. Are they the only metals? No. All alkali metals and even magnesium and beryllium in hot water will react. I know it doesn't say that on this table, but for our test, we're using this table. So I'm going to say calcium is going to become the ion. Even with water, it doesn't have to be an acid. It could be an acid. It'd be a violent reaction then. So if I write it this way, and I think of it as a single displacement reaction, I'm tempted to write this. And that is not correct. But if I write it this way, and recognize that calcium is only replacing the acidic hydrogen, not the hydrogen that's part of a hydroxide, the other one, I'll know that I need, calcium is going to form a +2. I'll need 2 hydroxides. So I must need 2 waters, 2 hydroxides, and then these guys become the hydrogen gas. So the hydrogens that are the acidic hydrogen, if we were doing an acid-base reaction to make water, become the gas. The hydrogens that are part of the hydroxide stay part of the hydroxide. Okay, calcium's a metal. It doesn't suddenly have a charge on the left. Water is a covalent compound. Write it together and give it an L. Calcium hydroxide is a strong base, so it breaks into ions. And hydrogen gas is a molecule. It stays together. All molecules stay together except for acids. Strong acids are ionized by water. They're pulled apart into ions. Okay, did anything cancel? No, nothing cancels. This calcium is a solid. This calcium is aqueous. Yep, there we go. And the last one, potassium, hydrogen carbonate, and acetic acid. Potassium's a +1. Hydrogen carbonate's a -1. Carbonate was a -2, but hydrogen carbonate's a -1. So they come together in a 1-to-1 ratio. Acetic acid, acids come from 8s. Here's acetate. -1 charge here. Means I need 1 hydrogen ion. Okay. Give you a second, maybe not a lot of you got to 10. Go ahead and work on that one.
Is HC2H3O2 not insoluble?
Well, it's soluble, but it's a weak acid. And weak acids we write together. It's not a salt, so we don't use the rules at the bottom. It's an acid. We use the rules for acid.
Gotcha.
Yeah, but it's a real common mistake that people say, look at acetic acid and say, oh, acetates are soluble. And if they're soluble in salts, they break apart. This is a soluble weak acid, so we can't see it, but it's weak, it stays together. All righty. Are there any questions?
I have a question about another worksheet after this.
Okay, but are we done with this one? Okay, it's a wrap.